Hi, we're the Fluoride Auto Sub-Team, and this semester we've been working on developing an absorption model to describe coagulant-fluoride interactions for fluoride removal using polyaluminum chloride for drinking water. I'm Desiree.
I'm Melissa.
I'm Emily.
And I'm Dominic. So as most of you already know, fluoride in moderation can be very beneficial in drinking water to human health. It can prevent tooth decay and even over time strengthen teeth. However, an overexposure to fluoride can be quite detrimental with a wide array of health detriments ranging from dental fluorosis to bone deformation and in some of the most severe cases, neurotoxic effects on cognition. As Agriculture hopes to build more water treatment plants in India, it's important to look at the geology of India. And as you can see from this map, there's a really high concentration of fluoride present in the groundwater of India. And with over 85% of India's drinking water sourced from the groundwater, this presents a potential health crisis. So it is Agriculture's goal in order to help mitigate this health crisis to determine how polyaluminum chloride can co-precipitate out of drinking water with fluoride in agriculture treatment plants. So in order to achieve this goal, the team first had to redesign our experimental apparatus. So one of the first changes we made was extending the length of our flocculator tube. So the flocculator tube is where polyaluminum chloride and fluoride interact and coalesce together. And by extending it by about 2 feet this semester, we were able to provide a longer residence time for the water in which the two could react together and more effectively and more efficiently form flocks. As you can see from figure 2, this is our experimental apparatus, which is meant to mimic the way that water, and especially in this part of the treatment process, will move through an agricultural treatment plant in the field. So this new sedimentation tube was changed by altering the position of the flock weir. And the flock weir is where the flocks will move out of the system. So basically flocks come into the bottom of the sedimentation tube and they build up forming a flock blanket, which is a thick layer of flocks that have formed together and stacked on top of each other. And as they exit that, it is our hope that there'll be a much lower effluent concentration of fluoride that moves out past the plate cellars and above. And so by changing this flock weir placement, we were basically just experimenting with the efficiency of the system. Another change we made was adding a new bottom geometry, and this is basically a sort of filter that is put on the very bottom of the sedimentation tube, which alters the flow patterns of flocks and the size of the flocks that are entering the sedimentation tube, which, as Desiree will talk about later, changes the results of our experiment.
This is our experimental apparatus, and how it works is water flows into the system where it then gets mixed with fluoride and coagulant. And in each experiment, we set our fluoride and coagulant concentrations using Crocota, and then that mixture goes through the flocculator where flocks form, and then that goes into the sedimentation tank, and the flocks build up into a flock blanket as Dominic described, and leaving at the top of the system is the clean water with a lower fluoride concentration than the influent, and then that goes through the turbidimeter and the fluoride sensor where we can measure the concentration of fluoride in the effluent stream.
So at the beginning of the semester, we weren't sure if the fluoride probe could detect fluoride in the form of flocks or if it could only detect fluoride in ionic form. So to test this, we collected high turbidity effluent. The high turbidity indicated that flocks were leaving the sedimentation tube. And then we tried filtering it through mesh that was in the lab. So this image shows our method of measuring the fluoride concentration. And our results are in this table. So as you can see for sample 3 and 5, after we filtered the effluent through the mesh, we saw that the fluoride concentration that we measured went up, and we think that this is because filtering through the mesh broke up the flocks and made into a form that was detectable by the probe. However, in sample 1, you can see that the concentration that we detected went down, and we think this is because at that point we were flushing out a large amount of gel from the tube, and that the flocks were so large that they were actually getting filtered out by the mesh as opposed to broken up. And so from this test, we concluded that the probe cannot detect fluoride in the form of flocks, and thus the effluent requires the breakup of flocks through mesh. And so we added a mesh filter into our system in order to measure a more accurate reading of fluoride.
So as we continue to collect experimental data, we have been plotting this data on the linear absorption isotherm, And this isotherm was developed by the fall 2018 team, and it has data on it from summer 2018, fall 2018, and now spring 2019. However, we have faced many issues this semester, so we only have 2 points on the isotherm from this semester. But basically, what this plots is on the y-axis, there's the uptake, which is the milligrams of fluoride per grams of PAC in the influent stream, against the x-axis, which has the effluent fluoride concentration. And so we measure the influent and the fluoride concentrations, and basically what this can tell us is, in the future, what specific optimal coagulant dosage we want for an effluent concentration of fluoride. So right now we have an 87% R-squared value between the experimental and theoretical models, and we hope to get to a 90% R-squared value before we can use this to predict optimal coagulant dosages.
Yeah, so as Emily mentioned, we had a lot of issues during experimentation, and as Dom mentioned, we were experimenting with a new bottom geometry. When we first implemented the bottom geometry, we noticed that we weren't getting the same flocks in the sedimentation tube as we were before we had implemented it. So we then took out the bottom geometry to compare with some of the other teams that were using what we thought were the same bottom geometries and who were getting successful results. And we saw very quickly that we were not using the same bottom geometry. Main difference was the entrance into the bottom geo. So as you can see in this picture, the one on the left is the correct one, and it has a much larger entrance than the one on the right, which is the one that we were using. And so this smaller entrance, because it's smaller, it's increasing the flow rate up into the sedimentation tube, and so this was kind of inhibiting our flock formation, and it was also smaller, so we thought it might have been breaking up the flocks as well. And so since we had these smaller flocks in the sed tube, they weren't settling properly, and then they weren't making a really nice, fluffy, like dense flock blanket, and so essentially all the flocks were just moving up through the sed tube and out the effluent instead of exiting out the flock where we want them to go, so that was definitely an issue. So we'll have to get the new correct bottom geometry before we can run more successful experiments. And it wouldn't be the Fluoride Auto sub-team if we didn't have issues with our probe. At the beginning of the semester, the probe that we were using had been about a year old, and so it was kind of on its last legs, and so we ordered a new one mid-semester to replace it. And then we went to calibrate it, and we ran into some issues because we weren't able to get a really nice standard calibration curve. You can see in this table that our R-squared for trying to calibrate it was about 0.35. With a working probe, you can get to around 0.999, which is what we were looking for but clearly didn't get. And then on the right, you can see the output from Procota for what the probe's values were, and it was just essentially fluctuating between its maximum and minimum values. We were also just trying to see if it would respond to putting in different concentrations of fluoride, and that wasn't working either, and it also wasn't responding to any like movement or shaking, which is really odd because all the past fluoride probes we've used are very sensitive to that. So we had been talking with the manufacturer and with Monroe and determined that we just got a faulty probe, unfortunately, and so we had to ship it back. We got a new one just this week, right in time for us to not be able to run any new experiments and get new data, which was unfortunate.
So for the future, like Desiree said, we just got a new probe, so we're going to calibrate it and make sure everything works. So we also want to test upflow velocities between 1 and 2 millimeters per second. So in agua clara plants in the field, they use 1 millimeter per second, and in our lab, we've been using 1.5. However, we think that there might be another optimal upflow velocity between 1 and 2, and we want it to be low enough that the flock blanket can actually form and flocks won't exit the sedimentation tube, but also high enough that we won't get gel in the tube. We want to keep testing different PAC to fluoride ratios to see, to keep plotting on the isotherm and see how well it adheres to that model. In light of the experiments that we did with the mesh and breaking up the flocks, we're wondering if the Langmuir isotherm is actually valid, or if we should be looking at a different model based on that. And finally, we want to research safe disposal of waste for both fluoride and possibly in the future arsenic.
So if you have any questions, please feel free to reach out to us. Our emails are displayed below. And so yeah, thank you so much for a great semester, and thank you for listening.
Thanks.
Thanks.